Okay, guys, I think we're ready to start the final session of the first part, the final session before lunch as well, with Dan Heidinga. I'm very pleased to have you here, Dan, and thank you for coming. I can't wait to know what kind of horrible mud holes you've been poking around in the last few years with the Valhalla stuff.
All right, so we're here to talk today about Project Valhalla and bringing values to Java. Except that I should probably rename this to inline types, as the project has renamed values again. So I'm going to get this wrong continually throughout this talk. I'm going to say value when I mean inline type. You know, that's okay. Just mentally switch value to inline type anywhere I say the wrong thing. But I figure I've got a good excuse for why I'm going to get this wrong. Project Valhalla has been going on for 6 years now, right? If we look at the state of Valhalla, we talk about it starting in 2014, and I've been part of the expert group dating back to the start. And so I've got a long history of saying the wrong thing now, because we've all been calling them values and need to be renaming them. But that's a long time to be running a project, right? I've been working at IBM now for 13 years, involved in JVMs and working as a project lead for the Eclipse OpenJ9 JVM. And there's not many projects I've been involved in that have been able to run for 6 years, right? So kind of wondering what's going on and why don't we have our value types yet? But 6 years isn't even the whole story. If we look back, John Dwemovich was talking about IBM's packed objects prototypes back in 2012. Looking at very much the same problem space, solving the same kinds of problems in a slightly different way. And if we dig around a little bit, we see that Gil Tenne, Martin Thompson, and others were talking about object layout back in 2013. At least this is the earliest Git commit I can find for that. They're probably talking about it even earlier. And not only this, but if you dig around hard enough, you can find references to efficient class prototypes from James Gosling that date back to 1999. So this is not really a new problem in the Java world. This is a problem we've known about for a long time. So why are we looking at 6 or 8 years and counting to get inline types into Java? And what's this key problem that we want to solve? Right? In this room, we're well aware of the fact that Java is not friendly to dense memory, right? We want our memory fabric to be able to load in nice sequential blocks, and Java likes to send us bouncing all over the heap, right? The example I'm showing here is you've got some reference on the Java stack, you have a pointer into the heap, from there you've got a pointer to a hash table, from there you've got a pointer to an entry array, from there you've got pointers into the key and the value, and so to get the actual thing you care about, you might be bouncing all over the heap, loading cache lines, taking page faults, crossing NUMA boundaries, and there's a lot of cost, right? This is one example, but as we look at our heap, we really end up with references spread all over. Now the GC can help us with this. Things that get allocated at the same time tend to group together mostly as long as the life cycles stay the same, and there's other things that you can do with the GC to try to correct that locality. But that's not what I want to talk about, because those are sort of side effects, right? As we look at our memory, the problem we have is we want better, denser data structures. Cameron talked about the cost of latencies this morning to load and access your memory. And so I've got numbers from a Core i7, it's an older processor, but really what we see is, to get memory out of a register, maybe 1 cycle. To get it out of an L1 cache, maybe 4 cycles. To get it out of L2, you're talking more and more and more, until if you're looking at scaled things, if you're going to hit RAM, 5 minutes, right? Or local RAM is 3 minutes. To hit remote RAM across a NUMA node, you're 5 minutes. To hit, disk, you're talking days. Right? Memory works really well when things are nicely packed into their cache lines. When they're not, we're going to pay. Right? So the problem we're trying to solve is to take our arrays that look like this, the reference type arrays, and turn them into the inline type ones. Right? That's the core problem that Valhalla has been looking at, is how do we give you the denser data structures that you need? And now this doesn't sound like a problem for 6 or 8 years. And yet it really is, right? I'm going to keep coming back to it is actually that kind of problem because I've sunk that many years into it. As the expert group, we like to repeat the phrase, yesterday's solutions are today's problems, or to put it with a future focus, today's solutions are tomorrow's problems, right? As we've solved things, it works out great for the problem of the day, and it causes us heartache down the road as we try to design the next thing. And some of these problems are hard, right? You can take something, hack it in, deliver it, and then deal with the consequences forever. And so what we've been trying to figure out is how do you deliver something that gives you the dense memory data or the dense data structures you want without causing us more and more problems down the line as we look at other new features coming in, as we look at how we evolve the Java platform. And some problems are over-constrained, right? So let's jump into looking at some of those constraints. I'm going to argue that most of Java programming is about the collections APIs, right? Everything we do is we're putting data into some collection, you process on it, you take it out, you put it in, we're modifying collections, we're iterating over collections. And so today we have collections that are based on generics. They work really great with references, but if you try to take primitive data and put them in, you're boxing it. Really what you want is that array list backed by a primitive int array so that you've got the nice data structure you want. And so we need to have a solution for collections that works for inline types and gives you that dense layout for the backing storage that you want. Now, collections mean generics. And as a VM engineer, I generally don't like generics. Mostly as a VM engineer, I get to ignore them. But in order to solve this, we need to solve it not only at the VM level, we need to solve it at the language level. And that means figuring out how to make inline types work with generics. Now, the generics we have today use erasure, and love it or hate it, what that means is that we get away with one representation for a generic class. So we only load the code once. You can have lots of instances, but we only have one sort of class file for it that gets shared by everyone, which is great for not paying for footprint, but not so good for when you want to specialize the data structure behind it. And as we look at solving these collections and erasure problems, we also have to keep the rest of your applications working the way they do. You know, the code that you compiled on Java 6 or before, you want to keep those libraries working as they did yesterday. And there are key classes that we do want to migrate. Anything that was introduced as a value-based class, think, Javalang optional, would be really nice to be able to turn into a inline type. So the expert group hasn't done nothing over the past few years. It's done a lot of things. We really took a look at how do we attack this problem from two directions. The first was, what can we do if we look at just the bytecodes and the class files and hack it from that level to understand the problem space and to know what problems we need to solve. And then we took an approach that said, okay, if we sort of ignore the class library level and we hack as hard as we can on the VM, can we give you the flattening you actually want? All right, so we'll look at the models that we've worked through, and you can read more details of some of this in the State of the Lambda document that I had shown on the first slide. But the first model we looked at was, can we take a class file and hack the class loaders to specialize things at class load? Annotate class files, add whatever metadata we need, and we used our primitives as the proxy for our inline types. We said, look, can we hack things to get you to the point where you get the proper backing storage for array list? And we were able to make that work, but you give up a lot of things. You give up the relationships between these specializations. They became distinct and separate classes. And so there was no single generic way to talk about any collection of a particular type. And that brought us to Model 2. So people wanted to be able to do that, especially library writers. And so we introduced a new top type called any, so that we could do generics of bar any to provide a common supertype for bar int and bar string, so that every species or specialization of a generic gave us a common supertype. But then we ran into access control rules. Those species wanted to be able to talk to each other. They wanted to be able to access each other's private members, private methods, and they couldn't because the VM won't let cross-class private access. And we still came into this problem of there's no common erasure across, a primitive array and an object array. So you end up with situations where the bytecodes just don't match, where the APIs just don't match, where it doesn't fit together well. So we tried to take all this and combined it and said, look, what if we tried to do our specialization not in the bytecodes, but we did it in the constant pool? Which sounded kind of similar to what Cameron was talking about this morning for playing with the global constant pool, which is kind of interesting to see that we're attacking similar problems in slightly different ways. But the problem was the bytecodes, again, are not orthogonal. I can't use one set of bytecodes for all data types. And so we had to add prefix bytecodes that carried what the actual type information was so we could patch those in the constant pool. And that became a giant mess. Suddenly your interpreter and your runtime system has to deal with multiple modes for every bytecode. And it's just a painful problem. But this taught us a lot of what we needed to know about generic specialization, about what pieces needed to be patched and what pieces don't work. Then we moved on to MVT, and we hacked the VM. And we said, look, can we get flattening out of the VM in a way that we can give users something they can try and provide us feedback? And so we showed that, yes, it's possible to flatten in the VM, but the APIs we gave people were based on method handles. And we found that anyone writing any serious amount of code on this struggled and struggled and struggled. And so we didn't get as much of the feedback as we would have liked on how well the flattened data structures helped people. But it's not like we took our learning, wrote it down somewhere, and have been ignoring it. As we've been progressing along, the Valhalla expert group has been feeding JEPs back into the system. And a lot of this has been to simplify some of these problems that we've been dealing with, to solve the problems rather than having to solve all of these things at once. So we fed nestmates in to allow access between things that are compiled together or in the same nest, and that will help solve some of those private access problems. We fed in condi, which gives us constant dynamic, which allows us to compute properties about a class at runtime using dynamic information and store it in the constant pool, which is a good route for the JIT to optimize based off of. Constable to make it easier to spin bytecodes and to talk about constants. We're seeing things like hidden classes start to appear as a JEP. Sealed types, I don't know if that one came out of the Valhalla group or we're just glommed onto it as something we can use later on. But it's in our list as well, and potentially VM-generated bridge methods. There's a lot of these problems that we've been working on solving in ways that we can push them out into the system so we don't have to do all of this in one go. All right, so that's a lot of background to get to what our model actually is. And we're at a point where we have a model we believe mostly works. There are still some rough edges to it, still some pieces that need to be tuned out or tuned so that they're clearer. But we've got a model, and the motto for it is codes like a class, works like an int. And this has served us well as we've tried to push the flattening and figure out what the behavior of the system should be. And it's a model we keep coming back to. But it's not entirely true anymore. We've switched things up a bit. So our motto is now codes like a class, works like an int, and maybe also like an object. So we've made our inline types subclasses of object. And this is one of the key simplifications we found in our system because it allows us to use all the A bytecodes and all the object bytecodes. So instead of having to specialize across sets of bytecodes that are different and not quite orthogonal, there's no common compare operations you can use. They don't have quite the same semantics. We've said, look, we're only going to have to worry about the A bytecodes. It also means we can ignore some of the horrible differences in slots. So for example, longs and doubles take 2 slots and everything else takes 1. And if you're trying to deal with specializing across these kinds of things, you end up with some very unpleasant code. So by saying, look, we're going to push all of this into object references or A bytecodes, we found out that we have a much cleaner and better model, one we didn't really believe when we started, but now know is going to work. And so we call this L-world. And it's called L-world because of these signature types in the VM. 4 objects all use the L carrier type. All right, so what do our inline types look like? They have really sort of three major properties. The first one is that they're immutable. Once they're created, you can't modify them. They have no identity. And so multiple instances of the same inline type that have the same values are identically equal or indistinguishable from each other. And they are flattenable, right? This is the key thing we're aiming for, is being able to flatten the data so that we have the good memory density that we've been looking for. But I will point out, flattenable does not guarantee flattened. It means we can, as the VM, flatten them, but we don't have to. All right, so we'll start with immutability and dig a little deeper into that. So what does it look like to create one of these inline types? Well, they get allocated with a new bytecode. That new bytecode is called default value. So anytime you want to create an instance of an inline type, you run the default value bytecode. And so the code I'm showing in the middle of the screen here is the equivalent of a constructor. And it looks an awful lot like a normal constructor, but I'll point out some of the key differences. The first one being it's a static method. So that means it doesn't get past an uninitialized instance. It has to create that instance for you. It's called init, just like any other constructor, takes some parameters, and then it has to return the value. Because it's a static method, so you didn't pass it in, it has to give it back to you at the end. So I said they were immutable, and if we're running a constructor, how do we do that? Well, we start with our default value, which goes off, allocates something, and nicely zeroes the memory. So by default, the values you get for an inline type are all zeros. And this works well with the way the JVM likes to allocate things. It typically likes to give you back zeroed memory. So you get back your initial point, and then to set any of the values, you have to create a new instance. And so you run the withfield bytecode. And withfield takes the point it's given, the value it's given, and creates a copy of it, modifying the one value and then pushing it back on the stack. So what we have here is not one allocation, we have three. So in the interpreter, you're going to pay for 3 allocations in this constructor, sort of one per withfield operation. Now, thankfully, the JIT is able to see through this, and it will only create one instance of this, or 0 if it can get away with scalarizing it. But that depends on how inline things have gotten. All right, so we can create these things explicitly, but there's also a number of other surprising places that they get created, and that's anytime you create an array of inline types, all of the fields in that array, all of the elements in it, are instances of your point class or instances of your inline type. And so each one of them has to start out life initialized. Whenever you have an object that has a flattened field in it, that flattened field has to start out initialized, right? We can't have you read one of these things and have it be in an uninitialized state. So fortunately, because we flattened it and we've said that the default value for most things is 0, we get to just mem clear the memory like we would anything else and give it back to you. Now, there are cases, though, where there are costs to this that aren't obvious. And that's in particular for large value types, where the VM may say, look, the thing you're asking for is too large to flatten, so we're not going to do it. And that means that before we can give you back that array that you've asked for here, we have to run through the memory and assign a default value to it. Right? There might be a pointer backing that. It might be an array of pointers to your value. And so we have to run through the memory and assign each slot. This happens more with value types that are going to be larger, so too large for the VM to decide to flatten, or for things where you've asked for special properties so that you avoid tearing or other things that you may want, where the VM can't give it to you if it's flattened. So by aiming for the design center of this, you end up in a good spot, which is small values. One of the other interesting things that comes out of immutability is that you can't have a circular reference, right? So first off, that node class is illegal, it won't compile. And the reason for that is I have no idea how to size that. It takes an infinite amount of space. because that node class inlines a node class, which inlines a node class, which inlines a node class, and I have no idea where to cut. So I not only can't flatten it, I can't create it. Now, this one I can create on the other hand. So I have an inline class that has a pointer to an object, which holds its next field, and I can flatten this, pretty easily and pretty nicely. But I still can't create a loop here. And the reason for that is anytime I try to assign the next field, I by definition create a new instance. And this is a powerful property because it means I can create long chains of things, but I can never have a loop in them. Or never a loop that's going to cause me a problem in some of the operations we do later, like equality and comparisons. All right, so that's some of the properties of immutability and what that does for value types. Let's look a little bit at what identitylessness gives us and why this matters. So I put this up, and nobody's going to argue with this, that every instance of one is identically equal or is the same thing, right? We can change the storage location where that one may sit. I might change an array element that holds onto it. I might change a field that holds onto it, or modify a stack location. But I'm never modifying the value 1, right? The value 1 is what it is, and it's obvious when I say this for primitive values that this is the way it works. Now, based on our motto, remember, codes like a class works like an int, this has to be true as well, that my inline types, where I've created identical instances, where I'm trying to be careful with the word identical, I've created equivalent instances, they all have to be equals equals. But the JVM has to jump through some hoops to get there. And I'll show you why the JVM has to do this. And if we look at the code on this slide, we see, the top of it, I've created some object reference. And I'm checking, is that object reference equal to itself? And so that has to always be true. There's no reasonable model in which that's not true, right? We would be very unhappy if the JVM decided that reference equality didn't work anymore. And since we allow inline types to be assigned to objects, we need to maintain those same properties. And as an expert group, we argued about this one for a long time because I personally really kind of hate this. It would be very nice if the VM could just get away with saying, no, it's an inline type, and so any equality operation on it returns false. But there's just too much code in the world like this that we would break if we started to do that. And it would be a very hard user model for people to live with. And so you sort of get forced into testing equality in a different way. And the way that we do that is called substitutability. So we say two instances of an inline type are equal, and that's equals equals, if their fields are substitutable. So what defines when something is substitutable? Well, primitive fields are easy, right? If the two primitive values are the same, then they are obviously substitutable. Non-inline reference types are easy as well. We already have a comp to give us the equality on those, and it's just a reference equality. Now, unfortunately, for inline types, we have to recurse through them. And so inline types can show up in a number of places, and so we have to do some additional costs in equals equals to be able to tell whether you're dealing with a reference type, because they can show up both where they're typed explicitly as a reference type, or typed explicitly as an inline type, but they can also hide anywhere that you have an object reference. So my node class earlier could be pointing at another inline type, and so I would have to recurse through that as I was testing equality to see if these things are actually substitutable. And inline types can implement interfaces. So I have the same problem on any interface typed field or any interface typed or object typed field. So what you end up with is a big change in the performance model for equals equals. It went from a nice pointer comparison to something that now has to recurse through and do a structural comparison. So an example of this is I took my node class and I created two lists of nodes. As you can see, the structure for these two things would be the same. And then if I test that if A equals B, they have to be the same. But in order to do this, I have to recursively walk through the data structure as I'm testing that equality. And so it means that your performance model for where equals is has changed, right? Everyone writing that code that says if two things are equals, if not, call dot equals, and then dot equals will immediately do, equals again, are going to be paying double costs for things that deal with inline types. Now, hopefully most inline types are not this kind of deep recursive structure, right? The design center, again, is small values, typically people looking for numeric data and that kind of smaller thing, specialized floats and the like. So, but this is where that immutability comes back to help us, because I can't end up with a circle. So at least I know that, my equals is bounded. Yes. So we're going to have to see some changes in programming patterns. It may be time to retire that equals followed by dot equals followed immediately by equals pattern as we as we write our code. All right. So there are other identity operations that take part. And for solving each of these identity operations, we go back to the guiding principle that codes like a class works like an int, but also that these things are immutable, and so they don't have an identity to mutate. And so many identity operations are really caring about only the identity, right? Value types, we care, you have the value, and you might have a storage location, but they're not the same thing. And so we're able to say, look, values are all identically equal. You can't change the value. It means you shouldn't want to wait, notify, or synchronize on that value, right? What would you actually lock on in that case? We don't want to carry around a lock word in every value in case you might want to lock on it. And as we want to be able to scalarize these things in the JIT, we don't want to have to worry about tracking, is somebody else trying to lock or modify or work with this value. So we did look at being able to share a lock for all substitutable values, but this can lead to surprising deadlocks. If two people locked on the same optional value, they might deadlock because they're using locks in different orders than others are. And it leads to the same kind of horrendous secretly passing of locks around that we see people use intern strings for. So if anybody is locking on intern strings, don't do that. Please don't do that. You may end up being deadlocked on in places you didn't expect. And so for value types, we've just said you can't do that. Another one is finalizers and weak references and soft references and phantom references. We've said there's no way to know when the particular reference you're talking about, referent you're talking about, is dead. So there's no actual time to trigger that GC. So we might allow you to register a finalizer, but we'd never call it. So at that point, it'd be better off to make it illegal. And the same for reference objects. We would never know when the life cycle of one of these things was actually dead, and so we'd never be able to do cleanup based on it. Now, if you really had some reason to want this, you could embed an object in your value type and take a soft reference to that. But I still wouldn't advise playing those kinds of games. Now, something like system identity hash code, though, does work. Right? It's easy to define a clear and logistical semantics for that, and so we've done that by making it based on substitutability. We just compute the hash code based off of all the elements in there and give that back to it. Okay, so that's a bunch of the identity operations, but we said earlier that we want to be able to talk about inline types as though they were objects, and so that means taking some changes and exposing that into the type system so that other people can take actions based on whether they are dealing with inline types or dealing with identity objects. And so we introduced some interfaces. So every inline type will implement inline object. by definition. And so you have an easy way to talk about all the inline objects. So if you want some method that only deals with inline objects, or you want to be able to overload a particular method to treat inline objects differently than identity objects, you can do that. This also gives us a tool for generic specialization, which is one of the goals we've been pushing towards, in that we can specialize based on if you're an inline object or an identity object. And then we said, look, if I want to be able to talk about inline objects, I really want to be able to talk about the world of all the other objects, all the identity objects. And so we introduced an interface for them as well. So every class that's a reference object will implement identity object. That means the classes you wrote back in 1995 when you were starting programming Java, if you load them in a VM that supports value types, will end up implementing identity object. The exact mechanism for how the VM will do that isn't completely specified yet, but it does mean that you might see extra interfaces than you were expecting. So for all those test cases that check that you have exactly 4 interfaces that you implement, you're going to have to go and modify them. It's funny, the consequence of that didn't really hit me until I was at FOSDEM, and someone was talking about the costs of adding null pointer exception messages. And all of the test cases they've had to change, and all of the test cases their users have had to change, and all of these things that get baked into golden files, cause us problems and problems and problems. But that does leave out one particular class. We looked at this and we said, look, every subclass of object is going to be an inline object, or it's going to be an identity object. But this code is actually legal. People typically do this when they want some unique object to lock on or to share as a common lock. But what does that implement? If you want it to have a lock, you need it to implement identity object. But if object implements identity object, then everyone implements identity object. And so we're kind of stuck here. And the answer we've gotten to is it can't really implement either. And so we need to find some way to retroactively make this code illegal. And there are thoughts on how to do that. We can start by making it illegal today going forward. But we're going to have to find some kind of pleading in the VM to replace this with some other subclass of object for code that already exists. It means we're going to take your new dupe init sequence that was targeting object and change it to something else. All right, so we have immutable identity-less value types, and the reason we want these is, again, we want them to be flattened so we get our memory density. So how does the flattening work? Well, first off, the VM is free to flatten or not flatten any inline type. You can write a representation that flattens nothing, and that's completely valid. But there are times where the VM decides it can't flatten them because it's too large, or it's Tuesday and the VM doesn't want to flatten things on Tuesday, or whatever the answer may be. And so you need some way to deal with that indirection. And not only does the VM need to be able to deal with not flattening something, you as a user probably have cases where you don't want things to be flattened. And some of these cases are surprisingly performance related. If you're sorting a large array of values, it would be awfully nice to sort pointers to those values and then only move all the values once, rather than continually moving your values and moving a lot of memory around. And there's work done by Doug Lee where he's done a bunch of experiments. I think he did them in C at the time, just to see the different costs between sorting references or sorting structs. And so he's posted all the data online, and you can see that there are certain crossover points. Now, thankfully, Doug Lee's done a bunch of that work, and so he'll update Java util concurrent, and most other people don't have to. But there are points in time where you're going to care about whether you're dealing with the inline type or you're dealing with a pointer to it. Memory density at times may work against you. If you have a large, sparse data structure, you may want pointers to your value types rather than allocating a really large array where you're only going to care about one or two of the values. There may be times where you want to deal with null. Value types, of course, if you flatten them, there's nowhere to store null. And so anytime you want to talk about null or a value, you're going to have to talk about an indirection. Recursive representations, my node class from earlier, it would be really nice not to have to type that next field as object, but to have a particular interface where I can talk about that's unique to my value. And erase generics, of course. We need to keep supporting erase generics so that they work with value types. So this is the model we actually come up with, is that every inline type, which will be flattenable, is also going to have a companion interface. And that interface is sealed so that it can only be implemented by the value. So we now have our level of indirection here. We have the value type, v, and we have this sort of companion box that it carries around with it everywhere. And because I is sealed, when we get sealed types in the JVM, I don't know what the date for that is, nobody knows, but when it actually shows up, we can build on top of that and use that to say, look, there only ever will be one implementation of this. And so the language can use this feature when it's generating code to generate you better code. Unfortunately, the VM still needs to do a bunch of checks here. It's an oddity of the verifier type system that it allows you to pass anything as an interface. So interfaces get checked at runtime, and so it says, no point doing that check at verification as well, and so you can smuggle anything around you want as an interface until you actually go to use it. And so even with a sealed interface, you can still pass things around that are that interface, or that don't actually implement that interface. And so the VM and the JIT are going to have to find ways to do these checks, but boil them out, or do them optimistically enough that we never have to pay the cost for this. Okay, so normally when we say boxing, people get upset because it means an allocation. But here it doesn't. Here we're talking about a subtyping relationship. My inline class V can always be passed around as though it's an I because it implements the interface. And in order to unbox, we're really talking about a check cast that worries about null. So we're in a pretty good state for that. All right, so we've been talking about flattening, and one of the areas where we don't flatten, at least in our implementation, is in code like this when we run it in the interpreter. So if I was to flatten this, I would need to allocate some space on the stack, but I don't know how long length is in the interpreter. It might be passed in, it might be fetched from somewhere else, and so I don't know how much stack space I need to reserve for this. So the interpreter would then have to say, maybe I optimistically grab some stack space and I stack allocate these point objects. But then you end up in a case where you run out of that optimistically allocated space. What do? Do you fall back to heap allocation? Do you throw it out of memory? Do you keep growing your stack until you stack overflow? The only reasonable answer here is to fall back to heap allocation. And so if that's where we're going to fall back to, then we started there with the interpreter. We said, look, ending up with a whole bunch of complicated code to try to stack allocate inline types in the interpreter is a losing game. And so the interpreter will always buffer inline types onto the heap. It means that transitions between the JIT and the interpreter become a little more complex as they have to handle whether it's heap allocated or scalarized or stack allocated in the JIT. But that's okay. That's all complexity we can figure out. The interpreter just doesn't have the space to do any better.
In the current prototype, the default value is a special one, is a singleton.
Okay. Now, even if we wanted to flatten everything, I've said it a couple of times, we can't flatten everything. Some values are going to be too large to reasonably flatten, even though the sweet spot is 1, maybe 2 machine words. So if you're writing value types, that's sort of where you should be aiming, small numbers of machine words. Some may require atomic guarantees. Right, as your values get bigger, they suddenly become terrible. And so if we had two threads running array, writing values into, writing inline types into an inline type array, and one thread reading them, depending on the size of those inline types, the values being read may not be consistent. You can read values that were never written. This goes back to earlier versions of Java, which ran on 32-bit hardware and typically had problems with longs and doubles. Longs and doubles being 64-bit, it was perfectly valid for a JVM to write those as two writes, which meant that anyone doing data races could read impossible values. And this problem becomes much more obvious when dealing with value types, and it's going to hit way more people. Now, there's a data race in this code, but people are used to getting away with that. They're used to being able to write reference values atomically and not worry about it. And so we're going to find a lot of people very surprised when they run into this behavior when they're using value types. Now, as we've been talking about flattening, I'm going to introduce Q here, which I haven't talked about much, but that's the carrier type that we use for value types, for inline types, when we want them to be flattened, or we want to hint to the VM that this is the location you would like them to be flattened. And so those Q types, they all need to be preloaded. So the JVM is going to have to look at every class that gets loaded and determine what Q types it talks about and preload them so that it knows what size they are. We need that to know how to lay out fields for objects that have inline types. And there's also some cases where we want to do optimized calling sequences that may need to preload them to know how to reserve the right amount of registers and generate those calling sequences early enough. But this is not your secret, signal to get your classes preloaded early. It's not a general preload signal. It only works if the type is an inline type. If we go to load a class with a Q and it's not actually an inline type, we'll throw exceptions and your class will be marked invalid. Now, sorry, Claus, for all the work you've done on speeding up startup. We're going to start loading more classes at startup, which may or may not work well with the work that you've been doing. And we're going to increase the heap pressure, at least until things JIT, because all those queues are going to cause allocations. But all of this to say is the expert group's been working hard away at this. We have a model that we mostly believe works. It has some rough edges. There are some things that may have to change. So, why aren't we working on delivering this yet? And this is why. Generic specialization, right? This is the key thing we keep coming back to, is that in order to give you the answer you want, those flattened data structures backing your collections, we need to be able to specialize generics for your inline types. And we really want to make sure that our solutions to inline types today don't become significant problems or complications on our road to generic specialization. And so this is sort of the focus area of the expert group right now, is figuring out, does our model work well enough with the generic specialization that we can move forward more with it? So, and with that, that's the end of my presentation. So,
questions? This will be interesting. Just a long microphone.
So isn't it true that a number of the problems that you presented there, we do have the ability for the user to choose a reference type. So we have this companion interface, and we can say, this really large array, I know all about this, I would just rather have pointers.
yes.
Yeah.
Yeah.
And the other kind of point of contention is it an interface? We're still working on, is it an abstract class?
Yeah, I given the time limits, I didn't want to go through all the details
true.
there. There is work being done to say, can it be an abstract class? There's a lot of investigations into the existing primitive wrappers, and can we turn the existing Java-lang integer into the companion type for the, whatever the value type for an int would be. So.
Anybody else?
I have a question about immutability. Since one of the inline types can hold an object or reference to an object, does that instance of an object, is that effectively immutable, or could I actually change the values of that object?
The object
In itself?
in itself doesn't change. You're able to change. You're able to mutate that object. You're just not able to mutate the reference to the object.
Right. So I might have two instances of an inline type that are at some point equals equals, and then I go change a value.
No, the inline types would check the object identity for that object, and so as long as that object is the identical object, they will continue to compare equals. You can mutate inside that object all you like, but we're talking about the reference to it.
Right.
So.
This might turn out to be a stupid question, but initially, at least 1 or 2 years ago, it looked like that would be was something relatively simple. You know, you say inline class, blah, blah, and everything there is faster than before because it's efficiently stored. Now it seems that the language gets a little bit complicated because you have to consider all these special cases. So will we be exposed to all of this directly in the language?
So the piece that you'll get exposed to in the language is this. You'll have your inline type, and most of the time that's exactly what you want. There may be cases where you want to talk about the wrapper around it, and so that would be a thing you become exposed to.
Part of this really enables the migration story as well. So some of it you don't actually need to know about. So for new code, yeah, just write in line, be happy.
Well, with anything where we tell you to be happy, profile, and then be happy.
Hi, I have a question about the metadata representation. Where's the description of these types as it relates to when a type is actually sort of instantiated somewhere? Is there a class word? It's not a class word now.
So in the interpreter, when we put them on the heap, they look like any other object.
Right.
When we flatten them into another class, the description for those fields, at least in our implementation, we just inline that into the parent's description.
Right. So I was thinking if this opens up an opportunity for dynamic redefinition of types that we don't have today. If you are only using an inline type, you could have different representations of those sort of treated the same. Like for instrumentation purposes, you could say this point now needs a tracking field, and I can have a new type that is treated the same as, for instance, a point with another int field into it.
As long as you do that before we ever create any instance of that point, you could do it. But the minute we create an instance, the minute we've loaded that, we've started making decisions based on how to lay out other classes and other fields based on that. And
right. So dynamic loading of these types are not like the recommended way to do it, or how would you see that? Would you redefine an inline type?
Well, like any type, you can't add fields.
Not
right?
now.
So,
that's what I'm thinking. It's like this. Does this open up a new opportunity for us? Okay.
No.
Cool.
In fact, you can't subclass them because otherwise, one of the reasons you can't subclass inline types is we don't know how much space to reserve in any point that we want to write it into. And so anytime I've reserved space for it in some container, in some array, in something else, and you have something that's a little bit bigger, I don't know how to write that in without corrupting memory or having to do, Smalltalk had a become operation, for example, where it was able to walk the heap and regrow and shift and change the size of objects. But that's not something anyone's put on the table for Java at this point.
Right. So that's what I'm asking, because this is a problem that we want to solve. So maybe if there is a description somewhere for how this layout looks, it could be possible in some sense, but we can take that offline.
Yeah, we can take it
Cool.
offline. It's the same problem as any other class, though. So all right.
Any more questions?
Thank you.